So hello everybody, my name is Rachel Oliver and I am going to talk to you today about what is inside an LED. So an LED is a light emitting diode and this is a Nobel Prize winning technology. We're going to go beneath the surface of these exciting devices and find out a little bit about how they work. Okay, so let's think first just about lighting. So the reason we're excited about LEDs is that they are an energy efficient technology for lighting our world. For just the normal lights, I've got my lights on at the moment, that I'm using in my living room, and those kinds of lights, we can have LEDs. But why do we care about that? Well, as I say, this is an energy efficient lighting technology. And you'd be surprised to know the amount of electricity we use to light up our world. Across the world in 2013, there were 23 million gigawatt hours generated. That's a vast quantity of energy being converted into electricity and used for various things. And about a quarter of that energy globally is used per light for lighting. So the energy cost of lighting, and hence the greenhouse gas cost of lighting, is immense. Now, LEDs can really make a difference to that. Here are some facts from the climate group, who say that a global switch to energy efficient light emitting diode technology, to these LED bulbs, as an example of one, just here, a global switch to these LED bulbs could save something like 1.4 billion tons of CO2 and avoid the construction of 1,250 power stations. So these energy efficient LEDs can really make a difference to the sustainability of our society. And that's why in 2014, the Nobel Prize in Physics was awarded to these three gentlemen, Professor Amano, Nakamura, and Akasaki, three Japanese scientists who were the people who invented the blue light emitting diode, which was needed to enable the white LED bulbs that we use in our homes. So if you own an LED bulb, what might be inside it? Well, if you start off with something which might look a little bit like this, it looks a little bit like a traditional bulb that we might have been using for generations. But if we take off this diffuser, this polymer cap, we find something else underneath. It looks a little bit like a sort of golf ball or a ping pong ball maybe. But it's actually made out of a very important material. This is a yellow phosphor. And inside it, beneath the yellow phosphor, here you can see we sort of sawed off this phosphor cap. We have the LEDs. So there are, in this case, multiple LEDs in the light emitting diode bulb, and they're going to generate what looks like from the outside white light. But actually, if we look at the LEDs under the phosphor cap, they aren't giving out white light at all. They're giving out blue light. These are the blue LEDs that the Nobel Prize was won for. And some of that blue light is converted into yellow light by the yellow phosphor cap. And together, it gives the impression of white. So in fact, the LEDs themselves are emitting in the blue. You can see that most clearly in this picture over here because they're so bright that when we try and take their photograph, it just completely saturates the camera and looks white. But here we can see that nice blue color. Okay, so let's dig down deeper into this device. We've found these blue LEDs, there are several of them, and then if we zoom in on a single one of them, we've got a kind of polymer cap, and then inside here, this is the actual LED chip itself. Let's zoom in a little further. We're going to keep zooming for a while here. So now we're looking at this in the optical microscope, and we can see some metal and some different layers, and I've got them labeled as a P electrode and an N electrode. They're going to contact different layers of the semiconductor where the charge carriers carrying the electrical current through the light emitting diode are positive and negative. We'll talk about them a bit more in a moment or two. Let's continue to zoom in for a second or two though. So we've been imaging under the optical microscope, but now we're going to take a small section of this device and look at it in a higher resolution microscope, an SEM or scanning electron microscope. That image is showing part of the metal that's contacting the top of the device. It's not that exciting. But now let's look at this. We've actually dug a hole, quite literally, in the surface of the device. We are now literally burying beneath the surface. And now we're using our scanning electron microscope to look at a cross-section of the device. And we can see all these different layers. We've got two here labeled as P-type and N-type layers, where we're going to have these different positive and negative charge carriers. But for the moment, we're going to continue to zoom in. Okay. So we're going from our cross-sectional SEM image, zooming in on the most important part of the device, just between the P and the N layers. And now we're looking at this with a transmission electron microscope, which gives us even higher resolutions. And we've got lots of very different layers here. This is a commercial device, so it's quite complicated. I'm not going to try and explain every element of this commercial device, but the bit we're going to be most interested in is this part here, labeled as MQW, which stands for multiple quantum well. Let's have a look at that in even more detail. Okay, this is just to show you just how tiny these structures are. So these layers now are 2.6 nanometers in thickness. So a nanometer is a billion times smaller than a meter. And typically an atom is maybe 10 times smaller than that. So a single atomic layer in gallium nitride is about 2.5 nanometers. This is kind of 10 atomic layers of material, extremely thin layers. This is actually, though, the bit of the device that really gives out the light. And this is the bit we need to understand if we really want to know how an LED works. Okay, so I've been showing you up till now these zoomed in pictures getting closer and closer into the device. And now I'm just going to show you a bit of a diagram of the device. So what we've got in our LED, this is a more simple one than the commercial one we were looking at in the microscope. This has got all the key bits. We've got what we're calling P-type gallium nitride. In the P-type gallium nitride, electricity is carried by positive charge carriers. In the N-type gallium nitride, electricity is carried by negative charge carriers. And they're going to combine in this region here in the middle with these very, very thin layers of indium gallium nitride that are in my image from the microscope. Now, we've got quite a lot to understand here in order to unpick what's going on in those quantum wells. And the first thing I want to talk to you about to kind of take a step back and really understand the materials in this device is the fact that this is a semiconductor material. I don't know how many people listening are familiar with semiconductor materials, so I'm just going to take you through some of the basics in the next few slides. Okay, so we're going to talk a little bit about how different materials conduct electricity. And we're going to start with something really familiar, a metal. Okay, so I've got a really simple cartoon here, bit of a circuit, and electricity, when the switch is closed, flows through my metal and my light bulb switches on. And that's all very familiar. We know metals conduct electricity. I suspect many people listening will know that metals conduct electricity because of the way their bonding works. We think of metallic bonding as being this sea of mobile electrons moving around this array of positive ion cores. And the electrons can move about freely. They stick the atoms together, but they also can flow to carry the current. So that's a metal, that's a familiar thing. Most people, I think, will also be familiar with insulators. Now I've put an insulator in my circuit in place of the metal, and when I close the switch, the light bulb doesn't come on because electricity doesn't flow through insulators. Great, okay. What's happening inside the material? Well, we know that in insulators, often all of the electrons are involved in bonding the atoms together. There are no free electrons available to move and carry the current, so therefore no current flows and the light bulb doesn't light. What about semiconductors? Well, you might think of a semiconductor as kind of semi-metal, semi-insulator, somewhere halfway in between. Let's have a look at our semiconductor. So here I've got my semiconductor, and at a low temperature, if the switch is closed, no electricity flows, the light bulb doesn't light. But if we warm up the semiconductor, then we can see the bulb start to glow. So the conductivity of a semiconductor is going to depend on its temperature. With metals, we're quite familiar perhaps with the idea that when you get them hot, they get more resistive. But actually, semiconductors can be completely insulating at low temperature, but at room temperature or sometimes a bit warmer, then they develop some conductivity. So that's a bit different. Something interesting is going on with the structure of the material that gives a different sort of conductivity here. Let's have a look at what. Okay, so in my little cartoon I've got of a semiconductor here, I've got positive ion cores and I've got negative electrons between them providing the bonding. But what happens in the semiconductor when we provide some thermal energy is that some of those electrons come loose from their rigid positions in this kind of array of bonds and are able to move through the material to carry the current. Now, those electrons have escaped from their bonding sites and are moving, and they leave behind a gap, a place where there once was an electron and no longer is. And we call those gaps where there aren't electrons holes. And other electrons can move in and out of those holes fairly easily, okay? And that's another mechanism by which the current can move. And in fact, we think of that as not the current being carried by negative electrons, but we think of the lack of an electron as a positive charge. So the holes are positive charge carriers, which can also carry the current. So when I talked about N-type and P-type gallium nitride before, my N-type gallium nitride has lots of electrons that are free to move and carry the current, and the P-type gallium nitride has lots of these holes that are free to move and carry the current. So the concept of hole conductivity, of there being a gap where an electron might otherwise be, which acts as a sort of quasi-particle and carries the current, is a bit like this puzzle. I don't know if you've ever done one of these puzzles where you have to kind of sort out the picture, or in this case just a line of numbers, by moving the tiles always into the gap. And you can think of it here that the gap is moving across the screen rather than worrying about every individual tile. And that's like the positive hole, which moves the current through the semiconductor. Okay, so now we have some clue about the semiconductor materials which make up this LED. But to get to understand how light is emitted in these materials, we also need to know about the difference between different semiconductor materials. Here, between my indium gallium nitride layers, these very, very thin layers I've referred to as quantum wells, and the gallium nitride which surrounds them. So we're going to take our understanding of semiconductors a bit further to try and understand these indium gallium nitride quantum wells. So say they are the heart of the LED. This is the bit where the light comes out, and that's why I want to tell you more about them. Yep, very important structures. Okay, so back to something familiar. Let's talk about atoms, okay? Now we know that as we go through the periodic table, our atoms have increasing numbers of both protons and electrons and neutrons making them up. So if we think of something quite simple like lithium, we can think of it in terms of these shells of electrons orbiting around the central positive nucleus. And as we add more electrons, we fill up those shells, and we know that there are different energy levels associated with the energy states that the electrons can take within the atom. And we also know that each available state can only take 2 electrons. This atom here is fine, it's got 2 electrons in each available state, but I can't do this. I can't just bung another electron in where I happen to fancy it and have 3 in this state. That's just fundamentally not how physics works. Okay, so we're familiar with atoms, and we're familiar with bonding them together so that we can start to form compounds. And we know that when we do that, we create these different bonding and anti-bonding orbitals, so different states that the electrons are able to sit in. And as we bond together more and more and more atoms, we create more and more available states for the electrons to sit in. That's because when we're putting more and more electrons into the system, we can't have them all sat in the same state. We know we can only have 2 electrons per state. So when our system contains more electrons, we need a load more states. And as we put in additional atoms and additional electrons and we create states, those states must be getting closer and closer and closer together because there's more and more of them. So that once we hit the point where we have a crystal with millions and millions of atoms in them, we no longer have individual states. They've all effectively run into each other and created what I describe as bands. Okay? So our simple atom, where we had separate energy levels into which we would have 2 electrons in each level, we have now created, with the many, many electrons in our crystal, separate bands. Okay? And it turns out that electrons are allowed within the bands, and there tends to be a gap often between them where the electrons are forbidden. All that's saying is there are some energies where electrons can perfectly happily sit, and some energies where they can't. Now that sounds like a weird and unfamiliar idea, but if you imagine me like standing on a chair, I am perfectly stable, in a perfectly nice energy level, stood on a chair. And I can jump off the chair and I can land on the floor. And on the floor, I'm quite stable, in a perfectly stable state on the floor. What would be very difficult for me is to kind of hover halfway up the chair. I either need to be in my stable state on the floor or in my stable state stood on the chair. There's effectively a gap in the middle where I'm not stable. I fall down. Well, electrons in this forbidden band gap here aren't stable and will fall down into the lower band, lowering their energy. Okay? So the band gap is a really important property of semiconductor materials. Let's bring this back to the metals and insulators that we were talking about earlier, that I expect everyone listening is familiar with. Now, in metals, if we talk about a band picture of a metal, okay, we don't really have to worry about the band gap because the band itself is not full of electrons. And that means that there is space within the band for the electrons to move into different states. There's spare states to put the electrons in. So even when it's cold or when it's hot, there's still gaps in the band and the electrons are still able to move around and carry the current. It may get a bit more difficult for them when it's hot because of all the atoms vibrating and getting in the way of their motion, but there's always enough room within the band for electron motion to happen. An insulator, on the other hand, the bands are completely filled with electrons. Okay? And then this lower band is completely filled. We call this lower band the valence band. Then there's a great big gap, and then there's an empty band up here. And because the gap between the two bands is so great, that's a huge step in energy. So even if we provide, I'm going to wait for this to come around, quite a lot of heat, which might give the electrons energy to jump across the gap, they don't, because that gap is too wide. When it's cold, there isn't any energy to help them jump, and there are no circumstances, really, under which this insulator is going to conduct electricity. Now, if we come to semiconductors, in semiconductors, the gap's a bit smaller. And if we give it enough heat, we can give some of the electrons enough energy to jump across the gap. Once they've jumped across the gap, these electrons that get into the conduction band, sorry, this animation goes round and round. I'm just going to give it a sec. Okay, so once the electrons have got across the gap, they can move in this higher energy band here, the conduction band, and the ones which are down here in this band, well, we'll see again in a second that when we heat it up, we create these holes that we talked about. We're now seeing them in a different picture, and these holes provide the space for the electrons to move and carry the current. So we can see there that semiconductors have the opportunity to conduct electricity only at high temperatures. So I've mentioned that these two bands are the conduction band and the valence band. Okay, the valence band is the band where the bonding electrons mostly sit. Valence is to do with bonding. The conduction band, once they're in there, they're definitely going to be conducting. But remember, these holes, these absence of electrons, effective positive charges, also appear in the valence band. So there we are. We have an electron and hole there in the conduction band and the valence band. And you can think of electrons as being a bit like footballs. They like to go to the bottom of the conduction band and sit at the lowest energy possible. The valence band contains these holes, which are a bit like helium balloons. And helium balloons tend to float up to the ceiling or to the top of the valence band. So electrons, like footballs, sink to the bottom of the conduction band. Holes, like balloons, rise to the top of the valence band. Okay, we are nearly there to be able to explain our quantum wells. A long explanation. So, just like different atoms have different energy levels. Different semiconductors have different band gaps. Gallium nitride is a wide bandgap semiconductor, has quite a big band gap. Indium nitride is a narrow bandgap semiconductor, has quite a narrow band gap. And what we have in our quantum wells in our LED is actually indium gallium nitride. It's an alloy, a mix-up of some indium nitride and some gallium nitride, and maybe unsurprisingly, it has a band gap partway in between the two. But its band gap is definitely narrower than that of the gallium nitride, and that's what's important about it. Because we know electrons are like football. They like to roll down to the low energy place. And holes are like helium balloons. They like to float up towards the ceiling or the top of the valence band. So now if we come back inside my LED, well, I have my P gallium nitride, where positive charges, holes, tend to carry the current. I have my N gallium nitride, where negative charges, electrons, tend to carry the current. We use a bias to push the positives away from the P contact into the quantum wells and negatives away from the N contact into the quantum wells, just using an external voltage across the two contacts here. And the electron and the hole tend to get trapped in the quantum well. That's because my electrons have fallen down into the low energy place. So like the footballs rolling downhill and getting trapped in this sort of bucket here. And the holes tend to get floated up like helium balloons towards the top, the valence band edge. And when they're trapped together in that small space, then they tend to combine with one another and light is given out. So the importance of the quantum wells here is that they tend to force the electron and hole together into one very, very, very thin layer. The importance of that is that what we want is for the electron and hole to find each other quickly, okay, and to combine quickly, giving us some light, because we don't want them getting trapped at anything else that might have gone wrong in our device. We don't want them finding mistakes in our crystal, which is what I'm going to come on to talking about next, which might mean that we don't successfully get light out of the device. Now, why does that mean we need a quantum well? Well, let's say that I wanted to meet my friend, and I said to my friend, let's meet up in Cambridge. Now, Cambridge isn't a huge city, but still, unless I got a bit more specific about that, we might be quite unlikely to find each other. But if I said to my friend, let's meet up after lockdown ends in the reception area in the Materials Science Department at 27 Charles Babbage Road in Cambridge at 3 o'clock, hopefully we'd have a pretty good chance of meeting. So we're much more likely to meet if we define a small volume in which to meet one another. The quantum well, which is very thin, defines a small volume into which we enclose, trap the electron and hole. They become likely to meet and they're likely to recombine. Okay, so I said that there might be other things, other fates for my electron and hole, my positive and negative charge carrier, if I didn't get them to recombine quickly. And those fates relate to these things: defects, mistakes in the crystal. This is another transmission electron microscopy image of a real LED. It's quite a simple one in this case, but we can see that there are these great lines running through the crystal. And this is a picture of the mistakes that might be in the crystal. Now, the types of mistakes I'm talking about in the crystal are things called dislocations. Okay? The crystal I've got kind of schematically drawn on the screen here is not a gallium nitride crystal. It's a highly simplified crystal where I've just got one kind of atoms, blue atoms, whatever blue means. And they're meant to be in perfectly ordered rows that go on periodically with no mistakes whatsoever. And I should be able to just draw nice lines and all these atoms all lined up in their perfect rows. In fact, whoops, I didn't mean to do that. If I'm clever, I can get a pen and draw in some of these lines of atoms. There we go. So these are nice straight lines of atoms in the crystal, even if my drawing of them is a bit wobbly. Okay, and you'd expect it to go on like that if the crystal were perfect, with nice straightish lines of atoms like this going on for ages. But we can see that just here, the lines of atoms aren't straight anymore because this line of atom just stops, okay? And that is a mistake in the crystal. This line of atom ought to continue, but the crystal building has gone wrong and it doesn't. We're thinking of this as a 2D thing, but really this is a 3-dimensional crystal. So you should think of each of these little blue dots as a column of atoms extending into the page. So this is like an extra half page inserted into a book. And you could see the end of the page just where the red line ends. This is now a picture of a real crystal which contains some dislocations. And the image of the real crystal has been taken at atomic resolution, but then it's been processed to show the lines of atoms, or the planes of atoms, the pages in the book, like I've got drawn in the diagram. Hopefully, if you've got bright eyes, you might be able to spot them. I'm going to now, oops, sorry, these slides are a little bit beyond me today, show them up for you, okay? So we can see that this is an extra half plane and this is an extra half plane. Those are in a gallium nitride crystal. If I show up all the atoms in a gallium nitride crystal, the dislocations become a bit more difficult to spot. So actually here we're mostly seeing the gallium atoms. They're easier to image in the transmission electron microscope. And again, we're seeing, looking down the end of columns of atoms that extend into the page. But this is a gallium nitride crystal imaged at atomic resolution. It's very characteristic, these kind of beautiful hexagonal rings of atoms. This is the sort of shapes you get in the crystal of gallium nitride. And it's impossible, I think, without spending a great deal of time for you to spot the dislocation. But I'll draw it in for you. It's just over here, and we can see its atomic structure. This is an example from a paper in the literature. Here's the real image, and here is a nice model of it. And we can see the atomic structure, which is mostly made of these 6-membered rings, going wrong and being disrupted at this part of the dislocation here, the end of this extra half plane. Okay, so why is that a problem? What does that do to the emission of light from our LED? Well, it kind of depends what material you're looking at. In gallium nitride, we have a huge number of these dislocations, these defects. If you look down at the surface of a gallium nitride crystal and counted the ends of the defects emerging from the crystal, you'd find about 1 billion of them in a centimetre squared. And with that huge number of mistakes in the crystal, we can still make LED devices that last more than 50,000 hours. They continue bright, shiny for a very long time. Now, the same is true of gallium arsenide devices. They last a similar amount of time, but they have a density of these defects, a dislocation density, of less than 1,000. And the interesting thing is that if we take that gallium arsenide material and increase the dislocation density, not up to 1 billion, like it is in gallium nitride, but just increase it by a factor of 10, then they only last less than 100 hours. In fact, if you're having a bad day, you pretty much turn one of them on, it gets slightly hot and goes thut, and that's the end of your light emitting device. So gallium nitride actually is incredibly robust to these defects. It's one of the things that's really surprising about this material. So we've already said that what we want is to trap the electron and hole in these thin layers, these quantum wells, and have them combine with one another and give out light. What happens if we introduce one of these defects running all the way through the quantum wells? So when I showed the pictures before, say the TEM images of the real dislocations, we were showing them as an extra half plane, and then we saw the disordered rings of atoms. But that disorder runs in a line into the crystal, into the page. And this line I'm showing here is that line of disorder, okay, that would run all the way through the crystal from that dislocation. So that, where that line passes through the crystal, it's passing through the quantum wells, it's passing through the gallium nitride layers between the quantum wells, and wherever it does that, it disrupts the perfect periodicity of the crystal. Now, band gap is all about periodicity. Band gap and periodicity are intimately related. So where we mess up that periodicity, we create extra states in the band gap, and the electron and hole can combine by the electron kind of trickling down through those states. We no longer have a forbidden gap. We've got places in the gap for the electron to sit, And as it wanders from extra state to extra state, it gives out not light, but heat. And we don't want our LED getting hot because that's energy that we were hoping to use to light up the room that we're wasting as heat. Okay, so what we kind of expect then is that dislocations, these defects, will mess up the performance of the device. So that if we have an electron and hole in a quantum well that contains a defect, if they meet at the defect, we'll get heat out rather than light. Something must be stopping the defects from having this terrible effect on the light emission. And one suggestion for why gallium nitride LEDs work so well was that rather than this indium gallium nitride layer all having a lovely uniform composition of indium, that actually in some places it had loads of indium and in other places it had hardly any. And what we've said already is that the indium content of indium gallium nitride controls its band gap. So the indium nitride has a really low band gap, gallium nitride has a really high band gap, so that the bits with lots of indium in will have a low band gap. They are the low energy place to put my electron and hole. So my electron and hole are going to sit in these, what I've got drawn as dark orange regions, these high indium content regions, and be trapped. There are barriers, changes in energy, which prevent them from getting to the defect. So they'll recombine and give out light. It's also possible that changes in the thickness of the quantum well could have a similar effect. Now, the reasons for this are to do with exactly what kind of energy levels are available in a really thin structure like a quantum well. You remember I said it was only like 10 atomic layers thick. And it turns out that when you're down at really, really, really thin layers, their thickness affects the energy levels that the electron and hole are able to take, as well as the composition. So it could be that the electron and hole gets stuck in a wide bit, which also turns out to be a lower energy place for them to sit than the narrow bit of the quantum well. And again, there are barriers to them exiting this wide bit of the quantum well, so they don't go to the defect, they recombine, and they give out light. So that was the two hypotheses that people had about why indium gallium nitride quantum wells were really robust to the presence of these defects. And to understand them, they obviously need to look for those changes in the structure of the quantum well in a microscope. I'm a materials scientist. This is basically what materials science is all about. We want to understand the structure of the materials and why it gives materials certain properties and why that allows devices to perform as well as they do. Or maybe how we might change that structure to get better device performance. And we do this a lot with microscopes, not in general necessarily with a light microscope like this, although light microscopes are really useful tools. But you can't see things that are only 2.5 nanometers across with a light microscope. So we need, or 3 nanometers in this diagram, we need a transmission electron microscope, which is what we've been talking about all the way through. But that turns out to be a bit of a problem, okay? And the reason that turns out to be a bit of a problem is that the electron microscope has an impact on the quantum wells. Now, these are some of the really early pictures that were taken of indium gallium nitride quantum wells using an electron microscope. And you can see that the quantum wells look really quite blobby. And people interpreted that blobbiness as being linked to these changes in indium content that we said might be the key to understanding why these devices work. And everyone was like, aha, now we understand there are these changes in indium content. That's why these devices work. We'll engineer better changes in indium content. That's the way forward to make the devices even better. The problem was that that wasn't really the end of the story. So this is another picture of some quantum wells. They're quite difficult to see. It's a high resolution transmission electron microscopy image, and the stripes, if you can see them, are planes of atoms within the quantum well. You can see it's a little bit blobby, but nothing like as blobby as the last picture we showed. Now, what I'm going to try and do here is showing the movie with you, okay? So this is the same as the image I was showing you before, okay? I've got the quantum wells, a little bit difficult to see, but now what I'm going to do is I'm going to play the movie, and what we're going to watch is what happens to the quantum wells as they're exposed to the electron beam. So we're going to keep on taking pictures of the quantum wells in the transmission electron microscope by shining an electron beam on the sample, and watch what happens. Okay, and what you can see is as we expose those quantum wells to the electron beam, they just get more and more and more blobby. Okay, I'm going to take that back and see if I can show it to you again. So we can see with exposure, the quantum wells develop this blotchy contrast that we've seen before in the earlier TEM images. And suddenly everyone started to get very suspicious. Was the blotchy contrast really because the quantum wells varied with indium content? Or was it because the way we were taking the picture was actually changing the quantum wells? Okay, give me one moment and I'm going to come back into my slides, I hope. There we go. Okay, so we needed a new method to look at these materials. Now, there are obviously lots of different options for how you study materials, but the technique we came up with was something rather interesting. It's called atom probe tomography. In fact, we're using something called laser pulsed atom probe tomography. What we have here is a needle-shaped specimen, a tiny thin specimen, where we have made a needle which has an end radius of only about 100 nanometers. Okay? And we're going to hold that needle at quite a high voltage. Now, because it's a very sharp point, if it's at a high voltage, there's a very high electric field around this point. And if you apply a high enough electric field, it tends to force atoms to evaporate, ions in fact, to evaporate from the end of the tip. And what we're going to do in this case is hold it just below the threshold that would be needed for that field evaporation. And then we're going to hold it quite a low temperature and we're just going to warm it up a tiny bit with a laser pulse. And the laser pulse will encourage atoms to evaporate, as I'm showing on the screen, one by one from the tip. We need to get just the right amount of laser pulse because we just need to tickle it to kick off one atom. We don't want half the tip exploding, which does happen when the experiment goes wrong. And those atoms, one by one, fly along these trajectories, which are determined by the radial radius of the tip, and they hit the detector. Now, the detector is designed to be sensitive to the position the atoms land. Okay? And you can trace these nice straight line trajectories back to where they must have left on this end hemisphere, if you like, of the tip. So that's giving us a picture of where the atoms came from in the kind of XY space. We also want to know about the atoms going deep into the tip into the Z direction. But actually that's kind of simple because we basically get one, approximately, atom evaporating per pulse. And the ones on the top have to evaporate before we can evaporate the ones further down. So the sequence with which the atoms arrive at the detector gives us their Z position along the length of the needle. So now we've got the positions of all the atoms. But what we wanted to know about, okay, was the indium gallium nitride and how its composition varied. So we need the identity of each atom that has flown along these trajectories. And what's going to give us that is the time it takes for the atoms to fly, because the forces acting on all the atoms are the same, they're defined by the electric field, and heavier atoms will fly slower than lighter atoms. So the time of flight from here to the detector gives us the chemical identity of the atom. And to do that, we have to take a gallium nitride device, which comes from what I would call a wafer, a kind of flat plate of the gallium nitride crystal. And we need to make a 100 nanometer needle. And it needs to be possible to apply an electric field to it because otherwise we can't apply our bias and get our field evaporation going. So we need a kind of 1 or 2 micrometer long gallium nitride needle with, in the very, very apex, a region with the quantum wells in that's about 100 nanometers across. That is not a very easy thing to make. Here is our starting point. So we have an insulating sapphire substrate, makes it jolly difficult to apply a voltage. And then we have this thick layer of our N-type gallium nitride. This particular sample didn't have the P-type gallium nitride on the top, so we've just got our quantum wells on the top. And the whole thing is the sapphire substrate is itself a disc about 50 millimeters across, with a very, very thin layer of gallium nitride on top of that. And we're going to make our needle-shaped specimen with something we call focused ion beam milling. Basically, in an SEM, we use a focused beam of electrons to image, In a focused ion beam microscope, we can image with the ions, but we can also use them in a very, very exact fashion to sputter away, dig holes in the sample. Like this, where it says nanomachining, that's a hole dug with the ion beam. Or here where it says nano deposition, that is where we have used the ion beam to induce deposition of a metal, which we've done by introducing a metal containing gas and then breaking it down with the ion beam. So we can do all sorts of things with our focused ion beam. I'm going to show you a very brief run through of what we do. So this is actually quite a well-known technique for making samples to go into the TEM, which tend to be thin foils, like thin wedges, effectively. And there we do a platinum deposition, make a sort of platinum square on the surface to help protect the bit of the sample we actually want to look at. And then we use the ion beam to dig 2 holes, okay? And we make the ion beam bring the sides of those holes closer and closer together until we've defined a thin membrane. Okay, so here is a thin membrane, and we've used the ion beam, and we've cut down here and along here, and this is ready to extract out of the wafer. We bring in a very sharp needle called an omniprobe micromanipulator, and we use our platinum deposition to literally, like sellotape, basically, the thin foil sample onto the micromanipulator. We chop it free and we bring it away from the wafer. And we're going to put it, in this case, onto a steel post. So here's my membrane, here's my micromanipulator, and there's my steel post. And across here is my platinum strap that I've deposited using the ion beam, which I've now used to glue or sellotape the membrane to the steel post. And I can chop the omniprobe free. I have to kind of clean it up before somebody else can use it, get rid of the bit that's still attached. And then we're going to mill a square post of our original gallium nitride sample, strapping it down very nicely with platinum so we'll get electrical connection. And then we start to do what we call annular milling, which means like donut-shaped milling, milling away to get a thinner and thinner and thinner post. So here a sort of cylindrical post. And then we sharpen it, making our annular milling have a smaller and smaller and smaller inner radius until we have this very, very thin needle. So that's the finished atom probe specimen for one of our earliest gallium nitride atom probe experiments. Okay, and this is the sort of data we then get out of the atom probe. What I'm looking at here is the data that we've collected, reconstructed to make what is actually a 3-dimensional render, although I'm showing you a 2-dimensional image of it. Every tiny turquoise dot in this image is a gallium atom. I'm only showing you about a quarter of the gallium atoms because otherwise there would be an awful lot of blue everywhere and it'd be hard to see what's going on. I'm not showing you any of the nitrogen atoms in this indium gallium nitride for the same reason, because the nitrogens just dominate the whole picture. I am, however, showing you the indium atoms, all of them, and we can see our quantum wells, okay, about 2.5 nanometers thick, as we've said before. Now, you can't really look at this and say, is this quantum well perfectly uniform? Because this is actually looking through quite a big wodge of the quantum well. And it's also not necessarily great to be judging these things by eye. So what we do is some mathematical analysis. Now, the thing you need to know about this mathematical analysis, those quantum wells we're looking at there are 25% indium, and that's 25% indium on the metal sites. So a chemical formula would be indium 0.25, gallium 0.75 N, okay, nitrogen. But something like that, which is 25% indium, it's not that every atom is 25% indium and 75% gallium, obviously not. There are gallium atoms and there are indium atoms discretely, okay? And they are in a what we would call a uniform layer. We expect them to be arranged at random, okay? So that doesn't mean that you always have kind of perfectly spread out indium atoms. Sometimes if you roll a dice 10 times, you get 10 sixes. So sometimes you get the odd row of indium atoms all next to each other, and sometimes they're a bit more spread out. That's kind of what a random alloy looks like. So we can statistically analyze whether an alloy is really random by essentially chopping the alloy up into small blocks, here 50 atom blocks, and measuring the composition of each block. Okay? And we expect the compositions of the blocks to vary. We don't expect all of them to be exactly 25% indium because of the nature of randomness, because sometimes we happen in some areas to get a bit more indium or a bit less indium, just like you sometimes happen to roll 10 sixes. Okay, so but we can draw a histogram of how many blocks there are at each indium content. And we know that we'd expect the distribution of the compositions to be binomial. And we can compare what we really get, the actual distribution, with these binomial distributions. Here for a sample that emits in the blue, bit less indium, about 17% or so. Here for a sample which emits in the green, bit more indium, bit over 20%. Okay, so, oops, sorry. What we can see is actually the data is quite similar to what we'd expect for our binomial distribution, our random distribution. And if we do a statistical analysis, we find that the probability that these distributions are random is really quite high. What that's telling us is we haven't got any evidence for the formation of these indium clusters. We haven't got any evidence of the formation of these blotches that we thought we saw in the TEM, but that then we wondered whether they'd been caused by the electron beam. Okay, so I said compositional variations were a possibility, but we can't find them in the atom probe, and we're very doubtful of the data in the transmission electron microscope. So what about these well width fluctuations, which I said were another possible way of trapping the electron in the hole? Well, we did find those, actually both in the transmission electron microscope and in the atom probe. If you look at this TEM data, you can hopefully see that the bottom interface of the quantum well is rather sharp and rather smooth, and the top interface is much more blurry and bumpy. In the atom probe, we can create something we call a compositional isosurface. This is a surface which links points each of the same composition. Okay, and when we do that, we see again, this is the bottom interface is very, very smooth, but the top interface has these lumps in, very much. So these are a few nanometers across. These are exactly the sort of structures I'm drawing schematically here, which might confine the electron and the hole, prevent them from moving to the defects. Now, what I've got here is a theoretical calculation, a detailed quantum mechanical calculation, which shows where the electron and the hole might actually sit in a structure like this. And we can see here that this region where the quantum well is thicker is actually doing quite a good job of trapping the electron. The electron and the hole are trapped separately in these structures, and it actually turns out that the hole may not always be trapped at this well width fluctuation, that sometimes there are just randomly high indium content regions within the quantum well, which might trap the hole themselves. So you don't necessarily always need any kind of particular structure to trap the holes. It's just the fact that there is a random alloy, and sometimes you get a few indium atoms together, provides hole trapping sites. Okay, so that was getting really quite in depth into the physics of these materials. But I hope you've enjoyed a kind of tour of what's really going on inside one of these light emitting diodes, right down at the atomic level. We've learned that these materials have defects, but the defects are actually surprisingly unimportant in controlling their performance. We've learned that we can use really advanced microscopy techniques to understand the structures of these materials, and that only when we understand structure properly can we then start to engineer the structure to make even better devices than we already have. We've talked about the fact that indium gallium nitride is a random alloy, but that doesn't make it uniform. But that very randomness can be enough to trap our charge carriers, our electrons and holes, and stop them going to our defects. All of that knowledge goes into making the humble light bulb when it's a light bulb made with LEDs. Okay. Thank you so much for listening. If you want to learn more about the sort of work me and my team do in Cambridge on these kinds of materials, gallium nitride and materials like that, do go to our website. The address is on the screen here, okay? We also have an Android app, which is on Google Play. A lot of the animated GIFs I've been using today are part of the lessons in that app. And if you go to Google Play and search for LED Lab, like I'm showing here, you can grab a copy of our app if you've got an Android phone and have a bit of a play. Apart from that, thank you very much for listening. Hope you've enjoyed it.